Okay, so we're talking about the electronic transitions. Like we're interested in electron spectroscopy and what are the energy levels of the electrons. So for the most part, we're not always interested in the average energy of the whole hydrogen atom. And so what we do is we go to a different coordinate system, and that's the center of mass coordinate system. And the very cool thing is that when you go through everything, and I asked you guys to go through everything, you find out that the final answer for the center of mass coordinates and the relative coordinate between the two reduces down to the same equation. And the only thing that changes is the mass. And instead of using the mass of the electron, you use the reduced mass. All right?
And the difference is 0.000.
Yes, so when all is said and done, when I have the hydrogen atom, when I have the H atom, I have a proton and I have an electron. I mean, what I'm really doing is I'm solving for, some coordinate system right here. That this is the R of the center of mass, and then this is the R that points from the proton to the electron. And essentially, that the proton being almost 2,000 times heavier than the electron, and more massive than the electron, that the R center of mass is very close to the proton. Right? And so the radial coordinate between the two, you can write Schrodinger's equation for the electron. For the R coordinate, the separation of variables and everything, and using these new variables, you get H times psi. I'll just write the time-independent equation equals En psi n. Sorry, and then it's going to beep right at me. Okay? And the only thing that changes in this whole equation is the form of the Hamiltonian. It's minus h bar squared over 2 mu. Yeah. Times del squared for the radial coordinate times psi n of r. Plus, now I'll write this out explicitly. This is going to be k q1 q2, which is going to be minus e squared over 4 pi epsilon naught.
The k is the 4 pi epsilon naught.
Okay. And then it's going to be the R1, or just R, the magnitude of R between them. And that's times psi n of r equals En psi n of r. All right? So the only thing that's changed in everything that we've done is this one factor right there, and that's the reduced mass. All right? And problem 5.2 said, to two significant digits, find the percent error in the binding energy of hydrogen introduced by the use of m instead of mu. So before we used m, and now we should really use mu.
And we did that in class, and I had to put it on my paper.
Good, very good. And what it is the energy scales with the mass. If you figure out the energy, you go to the hydrogen atom energies, the energy scales like m. So what we're doing is we're going to take the ratio of m to mu, all right, to get the ratio of those two energies. And it only differs by 0.054%. So, not even 1%, a half of a tenth of a percent change in energy. All right, so it's not so big when you're talking maybe, chemistry at a certain level and spectroscopy at a certain level. But it certainly does start to come into effect when you start including higher level effects. Once you start including things like the relativistic corrections, and you start adding in a lot of the coupling, like the spin-orbit coupling and the spin-spin coupling, the fine and the hyperfine structure, you definitely have to use the correct mass. All right? So that was part A. Part B was looking for the difference in energy between the Balmer lines. All right? And so, you get the energy levels for the correct hydrogen atom using the reduced mass, And then you can get the boundary line energies by just calculating the energy of transitions. All right, but the next one was more interesting, C. All right, and C is this thing called positronium. All right, and so I was very embarrassed one time. I had never heard of positronium. When I was almost finished with my PhD, and I had never come across positronium. And what positronium is, it's a short-lived, atom, if you want, with a positron and an electron. All right, so you replace the proton, and you replace that with an electron. All right, and so it is still a hydrogen-like system. It's a positive with an electron going around it negatively. At some point, they will annihilate each other, but this also forms a stable system. And again, stable, you have to think on an atomic scale. If the lifetime of this thing is 10 to the minus 6 seconds, and I forget what the lifetime of positronium is, so 10 to the minus 6 seconds before it annihilates. Is 10 to the minus 6 seconds long?
Yeah, well, no.
Okay, well, it depends, all right? So typically, in an atom, that's right, it depends. So in hydrogen, an electronic transition, if it's electromagnetic and it's allowed, those transitions are on the order of 10 to the minus 14 seconds. Like an electron will make a transition from one level to another level. 10 to the minus 14. So if positronium lives before it annihilates, 10 to the minus 6 seconds, it is fairly long-lived compared to electronic transitions. So is it possible to have a positronium-type atom where there are transitions that can be made in energy levels?
And it's there for 1 billion times longer than it takes.
That's right, it's there for 1 billion times longer than it takes. So this becomes a real system that you can study and do all types of experiments on. All right? You can now find the bonding energy. We have a simple answer for what the bonding energy, En goes like mu now, all right? It's proportional to mu. And so if we want the ratio or we can find the percent energy change if you consider like En for just the hydrogen atom with M, which we know is 13.6. It's going to be the ratio of, it's going to be some combination of the mu's and m's. But when you do this, you find out that the binding energy of positronium is like around 6 eV. All right, so you can form a real atom, positronium atom with a binding energy of 6 eV. All right, and then finally, the other system is that they talk about is muonic hydrogen, and that you go back to the proton, but instead of an electron, you use a muon. And a muon is generation 2 electron. So it's essentially just an electron that has, I think it's 206 times the mass of the electron. So what's the only thing that changes here? Versus it's the mass of the muon, right? And so something's going to change. And it turns out that all the binding energies change and everything. And that problem...
Center of mass is much closer to the muon than it is to the electron.
That's right. That's right.
6.
Yep. And so everything changes there. And so you can calculate the binding energy and transitions and
Because
things like
muon
that.
and proton is only an order of magnitude of 10, whereas electrons magnitude of 2,000.
Right. And so what you wanted to do here is we have all those classic formulas for hydrogen, En and Rn. All you do is replace the M's by mu's and you'll get these things. So what do you think the Rn's are from muonic hydrogen? So Rn's are essentially the radial coordinate for the distance between the proton and the particle. Are they bigger or are they smaller for muonic hydrogen than regular hydrogen?
Smaller for muon.
They're smaller, and so that it's tighter. The muon is held more
The
closely.
masses are so much closer.
That's right. So the radial separation. And one thing I wanted to add there is, so indeed you can calculate some numbers, and the calculations are pretty simple. I posted the solutions on the web for all these, so you can go over in more detail. But the radial separation is going to be much, much smaller. And I'll tell you about something that I have seen with muons is muonic H2+. All right, so it's H2+, but using a muon instead of an electron. All right, And so it's essentially,
Two hydrogen atoms, but only one.
well, two hydrogen nuclei, and then essentially
Just one muon between the two of them.
one muon between the two of them. All right? And with the muon being heavier than the electron, what do you think that if you figured out the separation between the two protons, would it be bigger or smaller? What you got, you know?
Smaller than if you have an electron.
It's going to be smaller. Everything's going to be
Because
tighter.
closer to the protons individually, so to combine them.
That's right.
It's
So everything's going to be smaller and tighter.
So
Right.
that looks very similar to He negative.
Right. Yeah, exactly. But you know, this is, you know, H2 plus is a stable molecule of hydrogen. This is H2 plus with a muon instead of the electron. And in Townsend, they talk about a paper and an idea to make cold fusion work. And the way they were thinking about making cold fusion work is that when fusion, what you want to do is fuse together hydrogen nuclei.
You want to use heavier and heavier electrons.
So use heavier and heavier electrons, and then the two nuclei will get closer and closer together. And then you increase the chances that you could have, you know, an overlap big enough so that you could have some type of fusion reaction there.
You want to generalize.
How?
Did you just look it up?
No, I know about it.
Oh, okay. So yeah, so this is real studies that people have done.
You have to have a level 3.
Yeah, go to a tau, all right? But it's hard to make tau electrons. I mean, yeah,
Well, yeah.
it's a lot harder. Okay? And then 5.3 was talking about the molecular energy space, and it looks complicated, and it is a little bit more complicated, but that problem just came down to really the definition of the angular frequency, which is essentially the square root of k over m, and in this case, the m is different, and so you change the angular frequency. Right? Okay, so let's go on. I really want to finish up today. All right, so we were talking about a two-body problem, and that, by the way, just so you know, it's a two-body problem, breaking it up into the center mass coordinate and the relative coordinate between the two. That's a two-body problem, and in mechanics, what you learn is the two-body problem can be solved exactly. All right, you can always solve a two-body problem analytically and exactly. But once you go to three bodies, so, you know, take a nucleus with two electrons, like helium with two electrons, it's a three-body problem. And as soon as you get to three, you cannot solve it analytically completely, totally. So the best we can solve analytically completely is hydrogen with the two-body, all right?
That's why you want to treat everything like hydrogen whenever possible.
Yeah, life gets complicated quickly, yeah. So the job of a physicist is often to look at a problem and say, you know, what approximations can I make to make this problem solvable at some level? And then as you get better and better and ask deeper and deeper questions, then you solve that problem at a deeper level. You know, so it's kind of, I always look at physics as a Taylor series expansion. You know, do I need the precision in my answer today out to the 30th, you know, Taylor series part, or do I need it just to the first order part? And that's what you're always doing as a physicist.
Yeah, didn't they solve the three-body problem recently, or someone had come up with some sort of?
It may be. The best, from what I know, the two-body was it. Your only hope of solving it analytically completely.
I heard something recently about that.
Yeah, I mean, there's all types of three-body solutions that will probably get better and better, but the question is it solved exactly?
Yeah.
And I always understood it wasn't solvable exactly. Okay, so the big thing is we did a two-body problem, and the two-body, each atom, it had two different things. It had a proton and an electron. All right, so they're not identical. So these are not identical. Okay, we next get into a big discussion with two-body, 2+ body, all right, not just two. But what we're doing is we're talking about identical particles. You know, for example, 2 electrons or 2 protons or something like that. All right? And so once we get identical, all right, we have a classical view of this. Classical view is that here's electron number 1, and then here's electron number 2. Alright, and let's say that I would do this. Let's do a coordinate system right here. Here's R1, and then here's R2. So what I'm going to do is I'm going to say, look, I could have a wave function A of R1, where A would mean something like this. When I say A, I'm just calling a general set of quantum numbers, whatever you need. So for example, if this were in 3-dimension and spherical, I would say this is NA, LA, MLA. So in other words, that A stands for whatever quantum numbers you need with that. And then over here, what I've had a wave function for with quantum numbers B, and that would be at R2. And I need this subscript 1 right there. So in our classical view, what we really have is that we have identical particles, but we also have in this classical view that they're distinguishable. And so the classical view is, look, these are particles. You know, if I had a good enough camera and I could see down small enough, I could trace this one and trace this one. They could collide, and after they collide, I could color this one blue and this one red, and I could watch the collision, and after the collision, I could see the blue and red ones go.
If they're both electrons, they wouldn't collide unless you made them.
Right, but we could follow that collision event. All right, and a collision event isn't talking about colliding, an electromagnetically scattered. But you could follow them. You could say this one went here. All right, and so if I were to build a total two-particle classical wave function, how would you construct one classically of two particles?
Is that?
Would I add them? Okay, and that's a big question, right? So think back about how we built the wave function.
You have to do vector.
Think about this. So for okay, what I'm talking about, let's build our wave function. All right, so let's stop for a moment. Classically, this is an independent space, right? It's an independent space. It has quantum numbers and it's at R1. And this is an independent space. They're completely independent of each other. So thinking about all our techniques on how we built up a wave function, right? When we had independent things going into a wave function. Well, yeah, but just think back to what we just did when we did spin. When we had two particle spin states. Like when we did the Clebsch-Gordan coefficients,
Right.
what we wanted to do is we said S total, MS total equals a summation, right? But what was our basis? What was the basis set?
Z basis.
It was a Z basis, but what did we we had Clebsch-Gordan coefficients.
Times the first one times the second one.
Okay, we had S1, MS1, S2, MS2.
So there'll be a summation over some number.
So my basic thing is, it's the product of these two independent spaces.
Summation of that product.
That's right. So the product of those two independent spins is what forms the basis. But that's one of those bases, and then we had to sum over all the different combinations that you could have of that product.
Right.
Okay, and I go back all the way to separation of variables. When I solve this differential equation through separation of variables, I multiply each separable part together, right? And then I construct a big, huge one as the product, and then I sum over all those possible products.
Right.
Okay? So we very definitely don't want to add together these two spaces.
You want the sum of the linear combinations, which means you have to find the product.
So we want the product, all right? So classically, if we were to come up with this total wave function, we would say something like this. Psi A of R1 times psi b of R2. All right, and then we would sum over, like, if you wanted to find a general solution, you would sum over all the combinations of A and B. All right, so that's what we expect on a classical. And if we wanted to follow this collision, again, this would be like red, and then we would see the red come up here, and that would be red, and then this would be blue, and then maybe after the blue would go over here. All right, but Griffith says some very nice things about this. All right, you can't paint an electron red or pin a label on it. It's inevitably and unpredictably altered state, raising doubts to whether the two had perhaps switched places. The fact is, all electrons are utterly identical in a way that no two classical objects can ever be. It's not that we just don't happen to know which electron it is, or which electron is which. God doesn't know which is which, because there is no such thing as this electron or that electron. And all we can legitimately speak about is an electron. All right?
They're fundamental particles, so they have to be the same thing.
Well, let's take it, it's fundamental, all right? But let's look at it. What does quantum mechanics tell us about particles? Are they hard balls?
No, they're waves.
They're waves. So quantum mechanically, the better picture is this. Quantum mechanical picture is maybe something like this. Here is psi A of R1. It's a distribution, right? It's a function.
Yep.
And then this would be psi B of R2. R1 and R2. But as these things overlap, right, and the wave functions are on top of each other, is it clear at all which is which? And so, in fact, you can't say which is which. All right?
You don't know if the first one's going back up or...
Yeah, it's a function. So stop thinking whether it's going back up or back down. Quantum mechanics says things are waves.
You can't tell which way the wave's going.
All right? Before you measure it, you know, it's just a wave. And after you measure it, it might be somewhere. All right? Before you measure it, it's this probability amplitude whose square means...
Further to the left, it's more likely to be the first one, but that doesn't mean
Exactly.
that.
Exactly.
Because it's non-zero anywhere ends. Right?
Okay, so what happens is in quantum picture, we have identical particles, but the key thing is that they're indistinguishable. Okay, and this forms a big basis of stat mech. So how many people have taken statistical mechanics this semester, or thermo? So it's thermostat mech, so this is a big topic of that. All right, now, without getting, I'm going to go into this a little bit more, but what I want to point out is this leads to Maxwell-Boltzmann distribution. Maxwell-Boltzmann distribution. And then this, it leads to two things. It leads to the Fermi-Dirac distribution for fermions,
And the Bose-Einstein.
and Bose-Einstein for bosons. For bosons, all right? And remember, what I mean by bosons, bosons are integer spin particles, and fermions are half integer particles. And the important thing is in limit toward classical, in the conditions here is that the wavelength starts to get, you know, on the order of d. So when I do an experiment, and the wavelength of these particles gets to be on the order of the thing I'm measuring, that these distributions reduce to the classical distribution. All right? So what's important to see is the quantum mechanical correct answer contains in its limit what we used to think was correct, which is the classical. So once again, this is kind of a correspondence idea. The quantum mechanics contains inside of it classical physics. All right? And the idea here, once again, is the following. is that, you know, if I have a wavelength like this, and my boat is this big, so this is my boat D. All right, let's see. So let me get this right. So this acts very
The
wavelength.
wavelength
The wavelength is much, much greater than D, it acts like a wave. But, so I might be the opposite direction here. Whereas if the wavelength, so I have two waves there, so let's make this a tiny wavelength. So two waves right
You're trying to
here.
get that line,
Yeah, and then this is
like
D.
anything.
Yeah, that's D. So this acts like a particle. So I have this wrong, where the wavelength is much, much less than D, then these things act classically. All right? Now, generally speaking, and D is the ballpark size of your experiment.
Yep.
All right? So classically, D might be the size of a detector, or your pixels in the detector. And even though those are on the order of millimeter, what are typically the wavelengths of particles?
Nanometers.
Yeah, okay, so wavelength equals h over p, like the de Broglie wavelength, right? And so h is 10 to the minus 34 joule seconds, all right? And p is MV, all right? When you plug those in, what is that wavelength you think comes out to be?
Still really small.
It's going to be incredibly small. So almost always, you're in this classical limit where these two distributions reduce down to here.
Should be much smaller than the wavelength of the light, you know, and its radiation.
That's right. Okay? Okay, so what we want to do is we want to investigate. What we're going to do is this that will lead to the Maxwell-Boltzmann, this view. So that view, that classical view of identical distinguishable particles will give us Maxwell-Boltzmann. All right? But it's the quantum mechanical view, so we want to come up with this. In anticipation, psi, I'll say fermions, and then psi bosons. Okay, those equal what? All right? And again, it will be this type of wave function that leads to Fermi-Dirac distribution, and this that leads to Einstein-Bose distribution. All right? But it's not clear right away what I should make those.
One's plus, one's minus, we don't know which is which.
Right, exactly. Well, yeah. Griffiths makes an argument right away that says that, look, my, and this is a good argument, that what matters in the end is not psi, but what? Probability. And so psi is psi star psi, right? So what he does is he wants to make a wave function that is kind of, it's fair to not knowing which is which, all right? But then when you square it, you get the same result. You get the same thing. Yeah, so in essence, what he did is he writes it the following way. That this is equation 5.10, is that psi, let's see, psi minus of R1 and R2 equals A times psi A of R1, psi B of R2, minus psi A of R2, psi B of R1. All right, and this one, psi plus, equals A times psi A of R1, psi B of R2, plus psi A of R2, and then psi B of R1. All right? Okay? All right, so let's argue this a little bit more. So let's get this at a deeper level,
Because, acid particles do not occupy the table.
Well, that is a result. So that is going to come out from this. All right? So, you know, some of the results of this, what do you get out of this? You get, as a result of the Pauli exclusion principle. All right? And then the statistics of Bose-Einstein, what do you get? Yeah, you can make a BEC. Alright? And so check this out, guys. If we just had the classical view of the world, we would never have any idea about the Pauli exclusion principle, and we would never have the idea that you can make a Bose-Einstein condensate.
So we wouldn't have lasers.
What's that?
We wouldn't have lasers.
We wouldn't have lasers, we wouldn't have atoms. We'd have all the electrons collapsing into the lowest energy state. You know, take carbon, it would be a 1s6, and we wouldn't have carbon, and we couldn't form life. So that by nature by the fact that we do have carbon, and we do have us, quantum mechanics is doing better than
Well, the understanding, without that understanding, you can't make a laser, it's not how it works.
We can't get there, yeah.
And we can't make a laser, we're, what, back in the,
Can't make
100 years ago.
Okay, so let me go over an idea, okay, where this comes from. So, what we're gonna do is we're gonna consider the following operator, P12, and what its effect is that when P12 acts on a function f, so let me see how you wrote it, f of R1, comma R2, is it switches it to f of R2, comma R1. All right. So, if
Some kind of operator that reverses the order of the radius.
if quantum mechanics can't distinguish two identical particles, right, then it has to be true that the Hamiltonian, you know, P12 on the Hamiltonian has to be okay. All right, so if I switch the particle labels, like R1 and not the labels where they're at, if I switch the radii, R1 and R2, then the Hamiltonian has to be invariant. It can't tell the difference between it. Because if that statement wasn't true, then it would mean that I could label which particle is which. All right? So we can rewrite this in the following way. So we can write this as P12 and then the Hamiltonian. And what must they do? That they have to commute.
So P21 Hamiltonian,
Say that again?
so that has to equal P21 for the Hamiltonian.
No, that's equal 0, so they can communicate.
Well, it would be like this, P12 on the Hamiltonian minus the Hamiltonian and then P12. So what it means is that if this acts on a function, the Hamiltonian is gonna act on a function, right? Where the function itself would have R1 and R2 changed, and then you'd have the Hamiltonian acting on that, right? And then over here, you have P12 acting on the Hamiltonian. So the Hamiltonian interchanges R1 and R2, but then it acts on F12. All right? Now, if the Hamiltonian is invariant to, you know, which one is which, this should all equal 0. This should equal 0. All right, that's a sub-argument. Now, if two operators commute, what does it mean?
Simultaneous argument.
Okay, they share simultaneous eigenfunctions. So share simultaneous eigenfunctions. Okay? So, here's a cool thing. So what we're going to do is we're going to look for the eigenfunctions of P. And if I find eigenfunctions if I find eigenfunctions of P, what do those have to be?
Eigenfunctions of the Hamiltonian.
Those have to be eigenfunctions of the Hamiltonian as well. All right? So here's how we're going to do it. We're going to consider P squared on psi equals lambda psi. Why did I write that equation?
So,
It's an
eigenequation.
It's an eigenequation. So I'm going to use this eigenequation to solve for the eigenvalues and the eigenfunctions of P. Okay? Everybody okay? Okay, so how am I going to solve it? Well, I need to go P squared minus lambda times psi equals 0. Right? And now what I need to do is I can go on, let's see, P squared minus lambda times minus 1 lambda times psi equals 0.
So you have to be writing settings.
What's that? I'm going to find 2, yeah. All right, and so now when I create P squared, all right, so here's how I often create P. Pij equals Ipj, so P squared, right? How I find the matrix elements of this. So this is, I'll rewrite this. This is going to be P11, P12, P21, P22, minus lambda 0, 0, lambda times psi equals 0. Okay? Okay, so here's the scoop. For P11, I'm going to have I, P squared, I. All right. So when I act, so I'll rewrite this as P, the operator twice. So when I act this operator P on I, it interchanges R1 and R2. But then when I come and operate on it again, what does it do? It switches it back. So this becomes I and this becomes I, so that is equal to 1. All right? When I have I, P, and then J, what do I get? 0. Because it's the integral of I and J, which is 0. Okay? Dot product of function space. It's the inner product. Okay, so this whole thing becomes 1, 0, 0, 1 minus lambda 0, 0, lambda, all times psi equals 0, or 1 minus lambda 0, 0, 1 minus lambda psi equals 0. And then what's our method for solving that?
Determinant.
Okay, you look for, you set the determinant equal to 0. So this can only be true for non-zero psi if the determinant of this equals 0. And when you solve this, the determinant of this equals 0, and you got to do it, so try doing it at home. You want the determinant of this equal to 0. And when you solve for that, what you get is lambda squared equals 1. All right, you get lambda squared equals 1. So lambda can equal plus 1, or it can equal minus 1.
How did you get 1, 0, 0, 1? Like what's that before you?
This one?
Yeah, that one.
I filled out the rest of the matrix. I did. Yeah. Okay. Okay, so the next big step is the following: is that I have two eigenvalues, plus or minus 1, right? So lambda equals plus or minus 1. You can have the, oh, sorry, no. So,
Give me 1 times 10 to the 20 squared equals 0.
Okay, so here's what it comes down to. And it ends up the following, so if we solve for this,
1 minus lambda.
it's not, it's 1 minus lambda squared equals 0.
So lambda equals 1.
So lambda only equals 1. So the p squared only has one eigenvalue. All right, which makes sense, right? Because p squared, when you act on it twice, it brings it back. All right, so what we get is that p squared times psi equals 1 times psi. So Dale, I screwed up. This only has one eigenvalue, and it's just 1. Because p squared acting on something, it switches R1 and R2, and then it switches it back. So it's got to get the same wave function back. All right? So I have p squared lambda equals 1. But recall that I have something like this. Remember that I have, recall that, L equals the square root of the L squared operator, right? Remember we have the L squared operator acting on y to the L ml equals h bar squared times L plus 1 y to the L ml.
Yep.
And what it means is that L equals the square root of h bar squared L times L plus 1. Okay? So here, what I'm going to do is I'm going to argue that p equals the square root of p squared. All right? Or in other words, that p equals the square root of 1, and the square root of 1 equals plus or minus 1. All right, so what I did is that my original goal was to find the eigenvalues and the eigenfunctions of p. I started with p squared, and I eventually got down to p, and I got the eigenvalues of p. So the eigenvalues of p are plus or minus 1. So what it means is that p acting on psi equals plus or minus 1 times psi.
Equals the operator.
Okay, yep, that means an operator. Okay, so the eigenvalues of p are plus or minus 1. What does that mean about psi? So now let's talk about the eigenfunctions of p. If p acts on psi 1, 2, and it switches them, and it gets the eigenvalue of 1, what does it mean about the original function? Okay, it means that the original function is 1 plus. So for example, if I act with the p operator on this, and I interchange R1 and R2,
You get a plus.
and I have a plus there, it comes out to be the same thing, and I get what eigenvalue? Plus 1. All right? So what it says is that the one of the wave functions for the parity operator has to be symmetric. And what I mean by symmetric is it's symmetric under the exchange of the R1 and R2. Alamar, you don't get it yet? That's okay. Okay. So these are the eigenvalues for the parity operator, just the parity. Right? So my claim, and remember what parity does is, so watch, let me try P, and I'll let me do it more explicitly here. P 1 to 2, all right, I'll put the 1 to 2 back in there, and it switches R1 and R2. So let's try P1 to 2 on psi plus. All right, that equals P1 to 2 on psi A of R1, psi B of R2, plus psi A of R2, psi B of R1. Okay, when you operate this on these, it switches R1 and R2. So what you get is psi A of R2, psi B of R1, plus psi A of R1, psi B of R2, right? Okay. So,
Which is the same.
which is the same, right?
Those stand weird.
So take this and put it over there, and it's just psi plus. So in other words, P12 on psi plus equals 1 times psi plus. Okay, so the first eigenfunction of the parity operator is symmetric. There's a plus there under the exchange of R1 and R2. All right, but remember, this has two eigenfunctions, right? Now, the other eigenfunction has an eigenvalue that's minus. Okay, so let's do that. So now let's do on psi minus and see what happens. Let's do the parity operator on psi minus, and what that does is it gives you this. All right? So now this term is negative to this one, and this term is negative to this one. So this equals minus 1 times psi minus. Do you see that? How many people see this? Okay.
Because it switches the negative side to the opposite.
Yeah, just plug it in. Just plug it in. So
Yeah.
psi minus. This
First term becomes
answer
negative.
is minus.
Yeah.
Psi minus.
It distributes the negative sign.
Yeah. Okay. So what we do is we call psi plus the symmetric answer, the symmetric wave function, the symmetric two-body wave function, and we call the psi minus the antisymmetric wave function. All right. Now, those are what the wave functions of the parity operator must be: a symmetric wave function, two-body wave function, and an antisymmetric wave, two-body wave function. What is our conclusion now about the solutions for the Hamiltonian
You have a symmetric.
of a two-body problem?
You're gonna have a symmetric and an antisymmetric.
There has to be two types. The world needs to have two types. So no longer is there just an answer to the two-body identical problem. You need two answers to the two-body identical problem. All right? And the two answers come in two different flavors. One flavor is symmetric, the other flavor is antisymmetric.
Which is why, when Schrodinger first tried to do his equation, and he got the psi squared and the relative, he didn't, he couldn't solve the relativistic. Because he didn't understand about the anti-electron.
It's certainly in there. But there are other complications there, okay? All right? To actually prove this, you do have to go to a fully relativistic treatment. All right? And Griffiths points out right here on page 204 the connection between spin and statistics. So the answer is that the minus, the antisymmetric, equals fermion wave function. And the symmetric equals boson wave functions. Okay? So the statement he makes here, the connection between spin and then the statistics that you get can only be proved using relativistic quantum mechanics. All right? In his footnote, it comes down to 3, and it says it seems bizarre that relativity should be necessary in this proof. But I don't think it's that bizarre, because spin is, after all, it's a relativistic thing. When does spin naturally arrive as the solution to Schrodinger's equation? Not when it's Schrodinger's equation, it's when it's the Dirac equation, which is relativistic. Okay? So this is called the spin statistics theorem, and it's great. Fermions are in Fermi-Dirac, antisymmetric. So let me say that again. Fermions have antisymmetric wave functions. As a result of antisymmetric wave functions, you end up with Fermi-Dirac statistics. And Fermi Dirac statistics don't let particles be in the same place at the same time with the same quantum numbers. That's the Pauli exclusion principle. Bosons obey symmetric wave functions. And symmetric wave functions, when you look at the statistics of it, you get Bose-Einstein statistics. And those show that under certain conditions, bosons want to be in the same place at the same time with the same quantum numbers, and that's a Bose-Einstein
Make
constant.
them overlap, increase energy.
Yeah, so let me see if I can come up with this a little bit, do some type of hand waving
We
argument.
started to discuss something similar at the end of the last semester.
Yes, exactly. Okay, so let's look at this real quick and see if we can make some type of idea about it. Let's look at this classical distribution. What matters is not just psi. What matters is the psi star psi. Okay? So if we go star psi here, we get CA star of R1, and psi B of R2 star, and then psi A of R1, and psi B of R2. Great. All right. Now let's look at these two distributions. So that's classical. This distribution, what are you going to get? You're going to get psi A star, it's a mess. R1, psi B, R2, and then it's going to be psi A, R1, psi B of R2, and then it's going to be minus, what is it going to be, 2 psi A, R1, psi B, R2. Well, okay, instead of doing that, I'm going to do it a little bit differently, all right? So I'm not going to go into all that. Let's do this. Okay, let's investigate what happens when R1 equals R2 and A equals B. All right?
Then this is both the same particle.
Okay, so they're the same particle, same place at the same time. This one becomes, so psi star becomes, so it's going to be psi squared, so it's going to be psi to the fourth. Psi to the fourth, we'll just call it A times R. Right? Okay, what happens to this one? When A equals B and R1 equals R2? Goes to 0. And what happens in this one? What do you got?
You get 2 squared, so it's 4.
Times 2, so it's 4. So you end up with 4 psi A to the fourth of R. So, what does it tell you? It tells you fermions, what happens in that limit?
So what happens?
Wave function goes away, what's that called?
Pauli exclusion.
Pauli exclusion principle. There's less chance you'll have particles in the same place at the same time, so you get a less number than classical results. What about if you have bosons?
4 times greater.
You get 4 times greater than classical. So you have this great thing. This is our world. Our world behaves like this. It doesn't behave like this. And the only reason that we have that, if you think about it, is because of this idea. So let's trace this all the way back. Why does our world need to have those two distributions? Two completely different types of particles, different behavior, bit different statistics. I agree, in a limit they look like this, but there's two fundamental. What is the fundamental reason?
Because the world's relativistic.
And not because it's relativistic.
Difference in bodies, how they can body probably to matching it up, matching it.
Okay, so getting there, it's the idea that things are made out of, are they made out of little balls that you can label blue, red, and green?
They were made out of waste.
Okay, that what we really are looking at is a world where
Yeah.
solutions are wave functions, all right, and things are not in a little tight spherical ball, that what things really are waves, right, and wave functions. Well, everything, you know, right now, as far as we know, everything, you know, really comes down to a wave
When we
function.
measure it, sometimes we get 0, and sometimes we get 4, what we thought we would get before. So there's-
Well, it depends. So the things are wave-like and overlap, right? Now you add in relativity, all right? And now you're going to have something to behave like this and like that. And so you're going to have those two distinctly different distributions.
Because everything is a wave, either gonna add it or pick each other up.
Yeah,
Basically, destructive and constructive waves.
Yeah, I mean, look, it all comes down that everything is truly wave-like. They're not little tiny balls that you can label and say, I know where you are, I know where you are. Toss that out. That idea gets the world wrong. It says there's just one distribution, and it gets it wrong. All right? So that's why this picture of the waves is so important, and that's why, you know, talking about the wave function is nice. Okay, so now let's go further. All right, and we can wrap things up.